Okay, so we're going to talk about symmetry and transformations. And in this particular lesson, in this particular video, we're going to focus on symmetry. We're going to look at three kinds of symmetry, and this is the first one. The idea of a functions, transformations of functions, and graphs of functions, symmetry across the y-axis. So when we say symmetry across the y-axis, imagine a y-axis, right? And imagine some kind of shape on the right side of the y-axis, like something like this. And if this graph has symmetry across the y-axis, then we're going to see basically what we call a reflection on the other side. Oftentimes it meets up at the y-axis, and so we might see something like this. And it'll look the same on the right side as it does on the left side. Okay? And so what I'm going to do is I'm first going to give you a technical definition of symmetry, something you can plug into a function. And then I'm going to show you how it works analytically. Then I'm going to show you what it looks like on a graph. Okay? So basically a relation, or in this case a function, has symmetry across the y-axis if the point xy, suppose xy is on the function f of x, well then the point negative xy is also on f of x, okay? What that means is this. So for example, let's say that the point 1, 5 is on f of x. So f of 1 is equal to 5, okay? Well, if the point 1, 5 is on f of x, then according to this, the point negative 1, 5. That means that the point negative 1, 5 is on f of x, so f of negative 1 is equal to 5. So the idea here is this, is that if you plug an x value into f and you get a particular output, you can plug the negative version of that number into f of x and get the exact same output. Another way of thinking about this is that f of, let's say, some value a is equal to f of negative a. They're the same value, and so this is a very sort of a useful way of understanding symmetry across the y-axis. So one way that you can apply this is by plugging it into. You might be given a particular relation. Like you might be given something like, y times x squared plus 3x squared is equal to 7. Okay? And you might be asked, well, hey, does this have symmetry across the y-axis? And so what we would do in this case is we would rewrite the whole thing, y, but in the case, every time you encounter an x, you would put parenthesis negative x. So it would be y negative x squared plus 3 times negative x, and then squared equals 7. And the question is this, does this relation or function, is it the exact same thing? Does it result in the same output? Okay, so since this results in 7, would this also result in 7? And so the way that you can understand this is that we know that x squared results in the same output as negative x squared. Okay, and one example of this is, let's say we plugged in 7 squared. Is that the same thing as negative 7 squared? Well, we know that 7 times 7 is 49, and we know that negative 7 times negative 7 is also 49. So whether you plug in 7 or negative 7 into this square function, you get the same output. And so what we can say is that this x squared term has the same output value as the negative x squared term. And this x squared term has the same output as this negative x squared term. And therefore, this statement is the same as this. We can exchange the x for a negative x, and it's still the same relation. And so that implies that this relation or function has symmetry across across the y-axis. And so what we're going to do now is we're going to switch over and we're going to look at a graph from Desmos, and we're going to look at it graphically. Okay, here's an example of a graph of a function that is symmetric about the y-axis. So here's our y-axis right here, okay? And so one side, the right side of the y-axis, looks the same as the left side of the x-axis, and we can sort of prove that this is symmetric about the y-axis because, here, let me get a pointer here. There we go. Because we can see the point, look at this, we have the point 1 and 0.5. We also have the point -1 and 0.5, okay, and that meets the criteria of symmetric about the y-axis. We have the point 2, 2, and we also have the point -2, 2. We have the point 3 and 4.5, and the point -3 and 4.5. And lastly, we have the point 4 and 8, and we have the point -4 and 8. And so you can see, graphically, you can see a picture that we have a mirror image. This side looks the same as this side, only it's a mirror image. And so this graph is symmetric about the y-axis. Okay, now we're going to look at symmetry across the x-axis. So this is vertical symmetry. So now we have an x-axis here. That's the x-axis. And so if we have some, let's say that we have some sort of shape up here, then we would actually wind up having the same shape down here. So you see there's the x-axis acts like a mirror, and we get the exact same thing above the x-axis as we get below the x-axis. And so what we can do is we can see how, let's say that this is the x value 4. And let's say that at an x value of 4, we have an output. Let's say this is the point 4, 2. Well, then this point is also on the graph, and this is the point 4, -2. And you can see here, this is the reverse of what we just saw with the y-axis symmetry, okay? So now, if xy is on f of x, and in this case, this is not a function, but it's a relation. We're going to call it f of x for now anyways. Then x -y is also. So we have the same x value, but now we have opposite y values. Before, we had opposite x values and the same y value. Now it's opposite y values and the same x value. Well, look, same x value 4, different but opposite y values, 2 and -2, okay? And if that is true, then the relation is said to have symmetry across the x-axis. And so this would be an example that you could see. You might see something like 5x squared y squared plus 3x minus y squared is equal to 12. Okay? And so what we're going to do is this time we're going to take the y values and replace them with -y. And so we'll wind up with 5x squared and then -y squared plus 3x minus -y squared equals 12. And the question we're going to ask here is this piece that we changed out, -y squared, is it the same as y squared? Well, yes, it is. We could make the same argument we made last time. If we put like a 7 in for y, 7 times 7 is 49. -7 times -7 is also 49. And so this piece here, even though we changed it from y to -y in both places, it still results in the same relation, and therefore this relation is symmetric across the x-axis. And so what we're now going to do is we're going to look at an example of a graph and see symmetry across the x-axis. Okay, here is an example of a graph that is symmetric about the x-axis. So here we have the x-axis, okay, and we can see that we have a similar shape. It's like, here's the top, and then it's like a mirror image underneath, okay? And we can prove that this is symmetric because look, the point 1, 1 is on the graph, and the point 1, -1 is also on the graph. So the x is the same, but the y goes from positive to negative, +1 to -1. Here we have the same thing. This point is reflected down here. We have the point 4, 2 and the point 4, negative 2. Here we have the point 9, 3, so over 9, up 3, and we have the point over 9, minus 3 on the graph. And then we have the point 16, 4, and then same distance down here, 16, negative 4, okay? And so we see that in all these cases, the x is the same, and the y value is the same magnitude, so like 4, but we have the positive 4 and we have the negative 4. And that indicates that this graph is symmetric over the x-axis. All right, so now let's talk about symmetry about the origin. In this case, the situation is if we have a function or a relation f of x, if xy is on f of x, if the point xy is on f of x, then f of x also contains the point negative x, negative y. And so, for example, if we have the point 5, 3 on f of x, then the point negative 5, negative 3 is also on f of x. Similarly, if we have the point negative 3, 6, then the point 3, negative 6 is also on the function. And so, graphically speaking, for example, let's say that this point right here is, let's say, the point 2, 3. Okay, so this is 2, 3. Well, then this point right here is actually negative 2, negative 3. Okay, so negative 2, negative 3. So we have x, y, and then we have negative x, negative y. Okay, and then let's say that this point right here is something like 6, 10. Then this point down here is going to be negative 6, negative 10. Okay, so basically every single point, every single xy point has another point that's just simply the opposite of x and the opposite of y, and that point is definitely on the relation. And so then the question is, how could we look at this analytically? Let's say that we had x squared plus y squared is equal to 1. Okay, this is actually the equation for the unit circle, and it's centered at the origin. So we already know that it's symmetrical about the origin. We also know it's symmetrical about the x-axis and symmetrical about the y-axis, but let's not worry about that right now. So what we're saying is, if we plugged in an x here and a y here, it would be true. The question now is, if we put in a negative x and a negative y, would it still be true? Well, we know that negative x squared is the same thing, will give us the same value as x squared. And we know that negative y squared will give us the same value as y squared. And therefore, the relation still maintains. It's still the exact same relation. And therefore, this relation, x squared plus y squared equals 1, is symmetric about the origin. Another great one that's symmetric about the origin is the function f of x equals x cubed. Okay? And a great one to plug in for x here is 2. So f of 2 is equal to 2 cubed, which is equal to 2 times 2 times 2. Okay? And that equals 8. So f of 2 is equal to 8. That means that the point 2, 8 is on this function. So 2, 8. So now we want to see, is the point negative 2, negative 8 on the function? Let's find out. What's f of negative 2? Well, that would be negative 2 cubed, which is negative 2 times negative 2 times negative 2. Well, negative 2 times negative 2 is positive 4. Positive 4 times negative 2 is negative 8. And sure enough, negative 2, negative 8, yes. So 2, 8 and negative 2, 8 are both points on the function f of x equals x cubed. And that means that f of x equals x cubed is symmetric about the origin. Now we're going to look at a graph of symmetric about the origin and see a little more of that. Okay, so here we have two examples. This is symmetry about the origin. And look, notice that if you go to the origin here, you can see that we have an up and then a down. And then the other direction we have a down and then an up. Okay? So in a way, another way to think about this is that we have an image of direction to the left that is the same, only opposite to the right, okay? And here, if we go to the origin, you can see that we have this over here, and then equal distance away down here is a reflection. Another way to think about it is you can pretend that there is a diagonal mirror that runs through the origin, and you can see that this is a reflection of this through this diagonal mirror. And you would get something very similar here, but it's a little more complicated to explain. But here, there's no way of getting this wrong. So this graph passes through the point 1, -4, and if we reverse both of these, reverse the 1, we get -1. Reverse the -4, we get +4. Well, -1, +4 is on the graph over here, -1, +4. 3, -8 is on the graph, and -3, +8 is on the graph. +4, -6 is on the graph, -4, +6 is on the graph. And lastly, +6, +11, and down here, -6, -11. We see the same thing over here. We have the point 2, 2, and the point -2, -2. We have the point 4, 1, and the point -4, -1. That's over here. This one corresponds to this one, and then this point corresponds to this one. We have 1, 4, and we have -1, -4. And so we can see evidence that this graph has symmetry across the origin.